Welcome back. Today we're going to talk about magnitude and orders of magnitude, which is we kind of abbreviate as So before we get into that, let's recall how we simplify something like this. So when we have the same base written in the numerator and the denominator, and we're trying to simplify this, we just subtract those powers. That's x to the 7 minus 3, which would be x to the 4th power. Same idea here, 3 to the 11th divided by 3 to the 6th is 3 to the 11 minus 6, which is just 3 to the 5th power. And then we can simplify 3 to the 5th power by actually typing that in and saying that's 243. So we couldn't do that with the x because we didn't know what x was. So, but anyways. All right, so orders of magnitude. Orders of magnitude is used to make approximate comparisons between two quantities. And when we look at orders of magnitude, what we're doing is we're taking something and we're saying we're going to use a base of 10 to kind of approximate this. But if I wrote something like this, 10 to the 11th power, that's a really big number. The order of magnitude here would be the 11. That would be the exponent. And so we can approximate things using that, but our base is always going to be 10 when we do that. So here's an example using the order of magnitude. But if the population of Solid High School is on the order of 10 to the 3rd power, that means that our is 3, that exponent. Notice how that's written with the base of 10. And the population of the city of Plano is on the order of 10 to the 5th, so our is equal to 5, and it has a base of 10. I want to find out the city's population and how many times as large that is of the high school. And the way I'm going to do that is I'm going to set this up as a proportion. So I'm going to say that the city of Plano, I'm going to say P to, well, I'll just Plano up here. This is the order of Plano to the order of SHS. Well, the order of Plano was 10 to the 5th power, and the order of SHS was 10 to the 3rd power. And now I have this set up kind of like what we had for our warm-up. If I wanted to simplify this or to figure this out, I need to say that that's 10 to the 5 minus 3, which is 2. Which 10 squared is 100. So therefore, the population is 100 times as large as that as the high school. And another way that I can ask this is I can say that Plano is how many orders of magnitude greater than the population of SHS. Well, remember, we had this. In the order, when we talk about the population, the order of magnitude, we would refer to that. The 2. So that is our order of magnitude. So 2 orders of magnitude greater. All right, so finding the orders of magnitude by evaluating the log of x and rounding to the nearest integer. So what we're going to be doing here is we're going to be typing these into our calculator. We're going to be saying, well, I'm going to say the log of x. Write this up here. What we're doing is we're saying the log of x equals our order of magnitude. Okay, so here we have the log of x, which in this case is 2,000. We're going to figure out what that equals, and we're going to round that to the nearest integer. So the log of 2,000 is equal to, I'm going to type this into my calculator. I'm not going to show it up here, but that's 3.301, blah, blah, blah. I just need to round that to the nearest integer, and I would say that that's 3. So the order of magnitude for the log of 2,000 is just 3. Another way that I can not write the order of magnitude, but how I can represent this exponentially, and remember, this is an approximation. Because, we're obviously rounding 3.3 to 3, so it's not going to be exact. But here, if I wanted to represent that kind of like I did in that population problem a second ago, where I'm trying to compare two quantities like I will in a second, then I can say that this is 2,000 is approximately equal to 10 to the third power, which 10 to the third power is 1,000 exactly. But we're going to be dealing with really big and really small numbers. So the bigger we get, smaller we get, it's going to get closer to that approximation, right? When you start talking about 8 trillion, then what really is 8,500,000 difference? I mean, when you have a number that large. Okay. Here we're going to look at the log of 4,000, and when I type that in, I had the log of 4,000. That gives me an order of magnitude of or comes out to about 3.6, which I would round to the nearest integer, which would be 4. So the order of magnitude for the log of 4,000 is just 4. And I just want to get in the habit of seeing something look this way, because this is kind of where we're headed. So our order of magnitude is 4 on that problem, and our order of magnitude is 3 on part A. But we're gonna look at this here in a second. Oops. Oh, I went the wrong way. All right, let's look at this. So we have the log of 0.002. What does that equal? The log of 0.002 is about negative 2.69, so that's going to round up to about negative 3. So our order of magnitude is negative 3. Once again, I'm going to write that this way and say that 0.002 is approximately 10 to the negative third. Here we have the log of 0.006, which is about negative 2. So our order of magnitude is negative 2. So therefore I can say 0.006 is approximately equal to 10 to the negative 2 power. All right, so here we have that how many times is quantity greater than. Remember, the orders of magnitude, by definition, like we talked about in the second slide, is looking at comparing two quantities. So when we compare these, this is where we're going to look at what I wrote whenever I said, whenever I had this written out like this. So we would say, 2,000 was approximately equal to 10 to the third power. 2,000 was approximately equal to 10 to the fourth power. That's a 4,000, not a 2,000. 0.002 was approximately equal to 10 to the negative 3 power, and 0.006 was approximately equal to 10 to the negative 2 power. So if I'm trying to compare these two numbers, or these two quantities, I'm looking at this as a whole. So if I'm trying to compare how many times A is greater than C, then I'm going to set that up as a proportion, A to C. And I'm going to use my 10 to the third power and 10 to the negative third power, which when I simplify that, I have 10 to the 3 minus a negative 3, which would be a plus 3, is 10 to the 6th power. So if I asked you how many orders it's greater than, you would say 10 to the 6th. But if I you would say 6, sorry. But if I said, how I phrase it here, how many times is A greater than C, then we would say 1 million times greater, because 10 to the 6th is 1 million. So this is 1 million times. Once again, if I say how many orders is A greater than C, that would be 6. If I say how many times is A greater than C, that would be 1 million. So how many times is B greater than A? Now we're looking at a proportion B to A. We have 10 to the 4th, 10 to the 3rd. That's just 10 to the 1st power, which is just 10. So it's 1 order greater, it's 10 times greater. All right, let's look at magnitude in earthquakes. A magnitude of an earthquake indicates the amount of seismic energy released or the size of the fault of the break in the Earth's surface when the sudden movement occurs. There's two log scales that measure the size of the earthquake, and one of them is the Richter scale by Charles Richter, and the other one's the moment magnitude scale by Thomas Hanks and Hiro Kanamori. All right, this video does not work, so I'm going to go to the next thing. All right, so to compare two quantities, or this is actually like to find the magnitude in earthquakes, we have this short little formula, log of x equals r, where x is the size of the earthquake and r is the measurement on the Richter scale. So this is, the Richter scale is the log of whatever that size is, and that's how that is measured. So what we're going to do here is we're going to compare two earthquakes and see how much greater one is than the other. So if I look at in 1989, an earthquake in San Francisco measured with the Richter scale at 7.2. So in other words, the Richter scale, 7.2, that tells me that the size of the log of San Francisco, I'm going to say that the log of S, because I don't know what the size is. All I'm giving is the Richter scale. Measures at 7.2. I'm going to set this up as a proportion, San Francisco to LA. I'm going to say S to L. And so from here, I could do the same thing for my LA one. So the size of the LA earthquake on the Richter scale was 6.3. And then from here, I want to set this up because I'm asking how many times larger is San Francisco than LA. I want to set this up to where I have 10 to the power of something. In order to do that, I need to get rid of my logs. And to get rid of my logs, I need to exponentiate using my base. When the base is not written, it is applied to be 10. So if I do 10 here and a 10 here, that's going to cancel those. And over here, this becomes S equals 10 to the 7.2. And over here, do the same thing, cancel those, and this tells me that L equals 10 to the 6.3. Now keep in mind, remember the S variable and the L variable from what we just talked about in the formula on the previous slide means the size of the earthquake, like how big the earthquake was. And our question is saying how many times larger was the San Francisco earthquake than the Los Angeles earthquake. So this is saying the size of the San Francisco earthquake was 10 to the 7.2, and the size of the Los Angeles earthquake was approximately 10.63. So if I want to find out how much bigger San Francisco was than LA, then I just do 10 to the 7.2 minus 6.3, which would be 10 to the 7.2, 7.2 minus 6.3. That would be 10 to the 0.9. So if I asked you how many orders it was greater than, we would say 0.9. But if I just say how many times it's greater than, I would say 10 to the 0.9. And I would go ahead and round that. And I would say that's 7.9. So I'm going to say that's approximately 8 times larger. And that is what we need to know about orders of magnitude. Good luck.